Hello Math 1224, this is Dr. P with Lesson Launch 903, A Rose by Any Other Name. We'll get to the reason for that title in just a few minutes. But first, I want to talk a little bit about what it means to graph, so graphing in polar coordinates. So you'll recall that when we graph in Cartesian coordinates, we think of y, the second coordinate, as a function of x. So we might, for example, say, let's graph the function y equals x squared, and the graph would look like something like this. We would say, well, this is my x coordinate on this axis is my y coordinate, and then if we're doing this using the elementary method of looking for specific points we can plot, then I might look at this equation and say, well, when x is 0, that means y is 0, and when x is 1, that means y is 1, and when x is 2, that means y is 4. And on the other side, if x is negative 1, then y is 1, and if x is negative 2, then y is 4, and so on. And we might surmise from there that when x is 0, y is 0, and as x increases from there, y continues to increase, and it increases faster and faster. And as x decreases from 0, y also increases faster and faster. And we might figure out then that the graph looks kind of like that, which is what we call a parabola. So that's the idea of graphing in Cartesian coordinates, is that at every time I am thinking of my coordinate along this axis, boy, red was a bad choice for that. I'm thinking of my coordinate on this axis as dependent on my coordinate along this axis. Now, graphing in polar coordinates is quite a bit different, although the basic idea is similar. So in polar coordinates, when I graph in polar coordinates, I think of r, my distance from the origin, as a function of theta, my direction. So I might say r equals some function r of theta. An example might be something very simple looking like r equals theta. Okay, so that's saying that whatever direction I'm thinking about, I take that radian measure, and that radian measure is going to be equal to my radius, or my distance from the origin. So what would something like that look like? Now you'll remember that if we graph a linear function in Cartesian coordinates, remember this is just a linear function because r is just equal to exactly what theta is. That's a linear function. That's just thinking about it numerically, it's like the function y equals x. But when we think about this in polar coordinates, something changes. So remember, my Cartesian plane is still based on the idea of Cartesian coordinates. I'm just going to graph points from this relationship here in that Cartesian plane. Okay, so now let's just sort of think about how things develop here. When theta is 0, my value of r is 0. And when theta is something like pi over 4, that means that my radius is going to be pi over 4. That's going to be something a little bit less than 1. So if I'm out along this direction, my radius is going to be just less than 1. And then when theta is pi over 2, that puts me along this axis. When theta is pi over 2, that's about 1.57. That means my distance is going to be about 1.57. And when I'm at theta equals 3 pi over 4, so I'm out along this axis here. Now the arithmetic's becoming a little bit hard for me to do, but I think that my r is going to be, well, it's going to be 3 pi over 4. I'm just trying to figure out numerically. That's about a little over 2, I think. And the basic idea is as we go along, as theta increases from 0, my radius becomes greater and greater. I get further and further away from the origin as theta increases. And the graph I'm going to get will look something like this. Now I'm sort of guesstimating here after a while. And remember, theta can advance past 2 pi, so this would be the point 2 pi comma 2 pi. But you got to remember, the second 2 pi means I'm in the direction 2 pi. That's the same as the direction 0. This 2 pi means I'm out at distance 2 pi. So this distance here is 2 pi. And this graph is going to continue. As theta continues to increase, my distance from the origin goes on increasing. And the graph that I create ends up being a spiral. In fact, it has a specific name. It's called the spiral of Archimedes. And it has some historical importance because, this is just a side note, because one problem that the ancient Greeks were obsessed with was the question of how to trisect an angle. Well, it turns out that if you have this spiral, if this spiral is a constructible object, you can trisect an angle. Like, for example, if I have an angle, say, from here out to here, I'm just going to draw a boundary there. Okay, there we go. So if I have the angle between these two rays here, and I want to trisect it, then, well, all I have to do is measure this distance here, because that distance is going to be the same as that angle measure, and then cut that distance into thirds, which is something that the ancient Greeks did know how to do using straight edge and compass constructions. And then once I have 1/3 of that distance there, I can just create a circle and then see where that circle intersects the spiral. And then whatever angle that is, that would be 1/3 of the angle I had constructed. I don't know if it looks exactly like that in this picture. I think I'm begging the users or the watcher's imagination a little bit. But anyway, that's the idea. I just thought I'd add that in there because I always thought that was interesting, this question of how you can use this object to trisect angles. But anyway, that's the spiral of Archimedes, and that's our first example of a graph obtained by graphing a relationship expressed in polar coordinates. All right. Anyway, here's another example. Suppose I want to graph the relationship r equals, how about if I did r equals cosine of 3 theta? Now, if I think about how r and theta relate, by the way, one thing that I can always do, I can always create a graph where my axes are theta and r. Now, that's not the same as what I did previously. What I did previously was I went directly from this relationship between r and theta to this graph, which was graphed on a coordinate plane where the axes represent y and x coordinates. Here, I'm just going to start by graphing this in the theta r plane. Theta r, not r theta, because theta is our independent variable here. Well, if I graph that in the theta r plane, then, well, my r starts at 1, because when theta is 0, I get cosine of 0, which is 1. And then gradually that radius is going to descend to 0, and then to -1. And then it's going to rise back up to 0 again, and then it's going to go to 1. Let's see, how much of this is going to happen in this frame here? I actually probably should want to, I'm just going to undo those, because I want to have this picture here run from theta equals 0 to theta equals 2 pi. And I think what I was doing there was going to make that difficult to do. So when theta is at 2 pi, this expression here becomes cosine of 6 pi. That is also 1. And I think from what I know about trig functions and what happens when I tweak parameters, that factor of 3 is going to take what would normally be 1 period here, and it's going to turn it into 3 periods. So I'm going to go from the crest down, and I'm going to reach the crest again twice. Wait, what did I do there? Hang on, let me try that again. Okay, a crest, and then another crest, and then I'm going to finally wind up back here. That's more like it. In fact, I can make that a little bit easier to draw by just doing it a little bit more carefully. I can divide that into thirds. That should be thirds. I don't think I quite did that well. But if that's 2 pi over 3 and that's 4 pi over 3, this is going to get awfully cluttered if I do it in green, so I'm just going to do it in a different color. There we go. Let's use blue. So I should have a crest here and a crest here, and I should bottom out halfway between each pair of consecutive crests. So I think I should get something like this. Now remember, this is a cartoon. I'm graphing this on my tablet and by hand, So that's a perfect storm of things that might cause inaccuracies here. But that's sort of the idea. Now that's in the theta r plane. What would this look like in the xy plane? That's the real question I want to answer. So I'm going to try and draw a big picture here. X, Y. And now I'm going to try and take what I have over here in blue and translate this into a picture where my height along this axis represents distance and my position on this axis represents what direction I'm in. All right, so let's start by just graphing some reference points here. Let's see, so this is 0 and 2 pi in terms of direction. This is theta equals 0 and theta equals 2 pi. If I want 2 pi over 3, that's going to be 1/3 of that. So I'm going to take this full rotation here, this full rotation, and divide it up into thirds. So I should get something like this. There we go. That's 2 pi over 3, and that's 4 pi over 3. Not bad anyway. I'm not sure I did that particularly well, but I think it'll get the point across. All right, now, when I'm at those three positions, when I'm at those three directions, those three values of theta, my radius should be positive 1. Positive 1 there, positive 1 there, positive 1 there. And then there are other places where my radius is going to read as -1. Now recall from the previous video, this is why I wanted to make kind of a big deal about it there, is that I can actually make some meaning of having radius -1. That means I go in the opposite direction for a distance of 1. So that's going to be, let me just mark that with a different color. This is going to be a very heavily annotated picture when we're done with it, but I think that's okay. That might actually help. So these correspond to the troughs in my picture. There we go. So when I'm at this position here, my radius should be -1. I should be out this way, actually. In fact, it's that point that I've already graphed there. And when I'm over here, I should be at this point here. And when I'm over here, I should be at this point here. So the question now becomes, all right, how in the world do we get between these points? All right, well, let's just think about what happens as I go from this point to this point. So as I go from r equals 1 to r equals -1. Remember, that was from here to here. So what's going to happen is, this is the greatest that my radius is ever going to be. As I start moving in this direction here, increasing theta, my radius is going to decrease pretty sharply. And then it's eventually going to reach 0. So should happen something like this. And then as theta continues to increase, I'm going to move out towards this point. Okay, so that's what happens from here to here. Now as I go from here back to here, I'm going to get closer to the origin, eventually pass through the origin. That's what happens here when r is 0. And then return to r equals 1, which is going to occur at this point here. So I should go like this, up, through the origin, and then over. And then as I go from here to here, I'm going to go from having radius of 1 back to having radius of -1 at this point. So I believe that's going to go like this. Now there's a lot of reasoning that I'm hiding here, and I'm not going to lie about that. One thing I want to tell you is that I don't expect you to get good in such a short time at drawing these polar graphs. I want you to have some idea of where they come from and what the reasoning is behind them. But what's typically going to happen is I'm going to give you a polar graph and the formula used to create it, and ask you to do calculus using both of those things, rather than having to create one from the other. But I wanted to show you this one because it's so cool. So this is actually the complete graph. I'm going to just trace it out one more time so you can see how this figure gets traced out. So I'm going to show what happens as I go from here all the way through here to here. Okay? And I'm going to try and call out crests and troughs as I go along. All right, so I start at a crest, and then I go through r equals 0 to a trough, and then back up through r equals 0 to another crest. This is r equals 1, and then back down to r equals 0, through another trough, and then back to r equals 0, through another crest, and then r equals 0, and then this is the final trough, and then I come back to this crest. I believe I've traced that figure out twice. That's what should be happening between here and here. It turns out that what this part of the graph does, or this part of this function here, it's identical to what this part of this function does. If this feels complicated, you're not alone. I had to think pretty hard about how to create this. So actually, one more thing I want to do. So I'm going to tell you, this is something I've never done before. Oh, before I forget, sorry. This graph in the very niche subsection of mathematicians who care about these things, this is called a rose. You might imagine why. It looks like a flower. Now, it doesn't look anything like a rose, actually. It's more like a daisy or something, but for whatever reason, it came to be called a rose. That's the reason for the title of this video. And roses can have 3 petals. This had 3 petals because I gave this a parameter of 3 here. If I'd made that a 5, it would have had 5 petals. If I'd made it a 7, it would have had 7 petals. And any of those would be called a rose. A rose by any other parameter is still a rose. And yes, if you're groaning, then that also means that you're pretty cool. All right. Anyway, let me just illustrate one more thing. You don't usually have to draw these by hand. There's an easier way to do it. I'm just not sure if I can do it and explain everything. So I'm going to try a little trick here. Here goes nothing. I have no idea whether this is going to work. Whoa, cool. I believe that's a live web browser. So let's see if I can go to Desmos.com. I don't even know if I'm still recording. I may just be talking to nobody right now. Yeah, let's see if I can go to Desmos.com. I believe I am still recording. I don't know if we've used this before or if you've used it before, but I love this. This gives you a very quick way to graph functions using your computer. So this is Desmos, and I'm going to try first graphing that first graph I showed you earlier, that r equals theta, the spiral of Archimedes. So let's see if I put r equals. So do they have theta here? That would be the real test, I think. Misc? No. Okay, never mind that. All right, this is quickly turning into a disaster. Let me see if doing this will work. Ah, there we go. All right, I'm having way too much fun here. Anyway, so this is the graph that we created earlier. You'll notice it has a distinct resemblance to what I did previously. Is that still up there? I'm just wondering if I start moving things around, can I still see? Oh, that's wonderful. Okay, so just a more sophisticated version of what you see up there. Let me see if I can move this over so it's out of the way of this graph. Because if I got the rows right, then that's really impressive, right? But for me to show that, I have to have this in a separate spot. Anyway, let me zoom back in on this here. Let's see what happens if I change that to r equals cosine of 3 theta. That's the other one. See, I think if I double click on the browser, does that make it go live again? There we go. All right. Anyway, so what if I put cosine of parentheses 3 theta? And it's looking, everything's coming up roses here, and that pun totally intended. If I zoom in on that, I get, I believe, exactly what I had before. And then I don't know if there's some easy way of tracing that out the way that I did earlier, but what if I put parentheses and then theta, comma, or actually, since this is polar coordinates, I need to do this in, how do I backspace on this thing? There we go. I need to put this in the order radius first, and then the angle. 3 theta. This is a little bit clunky, but man, I mean, just to be able to do this on a video is really great. Okay, that's not quite what I wanted there. Okay, comma. There we go. Theta. Let's see. Oh, too many variables. Okay, so I'm gonna have to work on that. See if there's some way to trace this out while having the graph up here. But anyway, now you see that is in fact the graph of r equals cosine of 3 theta in polar coordinates. But I wanted to do it by hand first so that you would see some of the reasoning that gets us to that point, because it is quite intricate. Anyway, what are we doing with all this? I realize there's been a distinct lack of calculus in the last 3 or so videos, but what's going to happen is we're going to start doing some calculus here. We're actually going to find the area inside of one of these petals, which, if that doesn't excite you, then I just don't know what to do with you. The fact that we can do that is crazy and cool and awesome all at the same time. But we will learn about that in our presentation on Wednesday. So I'll see you then. Thanks for watching.